In this video, we're going to talk about gas laws and the relationship between temperature, volume, and pressure. To start off, let's take a look at what these three things are before we know the relationships. Remember, temperature is the average kinetic energy of the particles of a substance. Let's add some gas particles into the simulator here to give us an idea of what's going on. Kinetic energy is referring to the energy of motion. Remember that? So look at how all these things are moving. They're moving in different directions, at different speeds. They're bouncing off each other and off the walls. Some of them are moving really fast, and some of them are moving really slow until they get hit by another one, and then they speed up, and maybe that other one slows down until another one hits it. They're all moving differently, so we average it. That's the average kinetic energy, and it results in a specific temperature. If we decrease the kinetic energy overall of the system, then the temperature is also going to go down. Likewise, if we increase the temperature, the average kinetic energy will be going up, meaning they'll all be moving faster. That's temperature. Volume is simply how much space does that sample occupy. It's the total of all the particles combined. For gases, we consider the volume of a single particle to be extremely small, and we don't count it for anything. But the total volume of the whole sample can be much greater. Finally, pressure. Pressure is a measurement of force. Force is about pushing and pulling. So pressure is specifically about the force of pushing. So every time one of these particles collides with the exterior of its container, it pushes it a little bit. The more often it pushes, the more pressure. The harder it collides with it, the more pressure. So pressure is the force of pushing. Okay, now let's talk about our laws. The first law that we're going to talk about is Boyle's law. Boyle's law is going to relate pressure and volume to one another. We have the equation P1 V1 equals P2 V2. So pressure, the starting pressure times the starting volume is going to be equal to the final pressure times the final. We'll work it out in an example in just a minute. Basically what this means though is that as the pressure increases, they move in opposite directions. This is called an inverse relationship. Let's have a look at how this works right here. So if I can change the volume of my container here, okay? So if I were to decrease what do you think happened to the pressure? The pressure goes up, right? Here it's at 19 atmospheres. If I increase the volume, look, it goes down to 13.4 atmospheres. Even bigger, even less pressure. Notice how the collisions with the outside are happening less frequently because they have more room to move. With less room, there's more collisions and therefore a higher pressure. We can look at this in terms of our equation, an example here. The way this has to work is that pressure and volume are going to change, then we need temperature to be held constant. So we're going to click on this right here, and that's going to hold temperature constant no matter how much I change the volume of my container. Okay? Notice again how by doing that, if I shrink this, that the pressure is going to increase even though the temperature stays the same. So in this example, it says if a 30 milliliter container is at a pressure of 2.5 atmospheres, how would the pressure change if the volume were changed to 20 milliliters? So we're decreasing the volume. Guess what's going to happen? Guess what's going to happen to the pressure? Well, we just experienced that. A decrease in volume results in an increase in pressure. You can calculate it exactly by inputting these numbers here into our equation. P1 and V1 are the starting pressure and volume. Here it is. If a 30 milliliter container at 2.5 atmospheres of pressure, right? So put those numbers in, 30 times 2.5. If we decrease the volume, that's the changed one. So that's the final volume. Put 20 milliliters into this side right here. Now you can solve for your one unknown. It's some pretty simple algebra here. Solve for your one unknown to get the final pressure. Okay, I'm not going to work it out for you. Let's move on. The next law is Charles' law. Charles' law shows the relationship between volume and temperature. Notice how the graph is different here and the line goes up. What this means is that volume and temperature have a direct relationship. Meaning, as one goes up, so does the other one. If we increase the volume, the temperature goes up also. If we decrease the temperature, the volume decreases. This happens when we have our pressure held at a constant. Only if our pressure is at a constant. Okay? So, we can do this. We can model this here by holding the pressure constant, and we can increase the temperature. All right. So, what do you suppose is going to happen here to the temperature if I increase or decrease the volume of my container? Let's have a look. If I decrease the volume, so too did the temperature. Okay? This has to happen if we hold the pressure constant. Okay? Meaning there's fewer collisions. So to have fewer collisions, we have to slow down the particles. If I increase the volume, then I can increase the temperature. Okay? This is in order to maintain that same pressure. So notice how, oops, wrong one here. Notice how all along the pressure is staying the same, but the volume and the temperature are changing. This is Charles' law, and you can work it out in this problem right here. If a 50 milliliter balloon at 250 Kelvin is compressed or shrunk to 10 milliliters, what is the new temperature? So just like the other one, all you have to do is figure out what's the starting volume and temperature and what is the final volume or temperature. So here, 50 milliliters is the starting volume and 350 Kelvin is the starting temperature. 10 milliliters is the starting volume, so solve for the unknown and you'll have the new temperature in Kelvin. Okay, next law. Gay-Lussac's law. Look, the graph is the same over here. The line goes up. That must mean that it's also a direct relationship. Or as one increases, so does the other one. So if we increase the pressure or the temperature, then the other one will go up too. But this only happens if we can hold volume at a constant. So let's try that out. Oops. Let's go here instead. Need to add some gas in here. Okay. So we want to hold volume at a constant, meaning we can no longer change what the volume is, but we're allowed to change pressure and temperature. Okay. So let's change the temperature by increasing the temperature. What do you suppose will happen to the pressure if we increase that number? Well, have a look. I'm applying heat and the pressure is going up and the temperature is going up. Likewise, if I move the temperature down, the pressure will go down too, and the volume remains the same. We can use our equation to solve again. It's P1 over T1 equals P2 over T2. So, a gas-filled container at 75 degrees Celsius, 130 kilopascals is heated to a temperature of 100 degrees Celsius is the new pressure. So there's something different about this. For one, the temperature is in Celsius. You're going to have to change that temperature to Kelvin. So reference the Celsius to Kelvin conversion scale. It's pretty easy. Just add 3 to your Celsius and you'll have Kelvin. The pressure is in kilopascals. That's okay. You can just leave it as 130. You don't have to have to change it to atmospheres. It works just fine this way. Okay? So put your numbers into the equation. 75 plus 273 will get you your temperature in Kelvin. 130 is your starting pressure. And then 100 plus 273 is your new temperature in Kelvin. Put that one in, and you can solve for your unknown of pressure. Okay, good luck on that. The last law that I'm going to show you today is the combined gas law. And you can see all three, both Charles and Gay-Lussac's, in this equation here of P1 V1 over T1 equals P2 V2 over T2. All three interact with each other. This represents a little bit more of a realistic situation where nothing is being held constant except for the number of gas particles in our sample. It's much more likely that all three would be interacting with each other. Notice here, if we increase the temperature, that the pressure will increase, but we could also increase the size here, which is going to cause some other changes to happen. Okay, so in a more realistic situation, if we increase the pressure, the volume could possibly change some, and the temperature could also change. All three of these are interacting with each other. Okay, so I hope you find this helpful in understanding how they work. I encourage you to play around with this. I'll send you the link, and I'm going to give you the questions as well, and I want you to try to solve those questions that I asked you in this video. So submit your answers in the form that I show to you, and I'll get back to you with some feedback. Send me any questions you have. Thanks, guys. See you later.